Okay. Thanks, Roger, for the introduction. First, I'd like to thank the organizers for inviting me. It's really an interesting and stimulating conference. Actually learned a lot. So today I'm going to tell you some recent developments in this area of Majorana Fermions in condensed matter. And in particular, I'm going to describe how one can control the Majorana Fermions using the charging energy in mesoscopic systems, in nanoscale systems. So this is what I mean, Majorana takes charge. I'll show you some very recent experiments towards the demonstration of some of the peculiar properties of Majorana Fermions. And then in the second of my talk, I'll be more speculative and describe some of our proposals on maybe Majorana Fermions can be a new kind of a qubit for quantum information with some desirable properties. So let me first acknowledge my collaborators. This work is done with my students and postdocs at MIT. So Sagar Vijay played a key role in all the works I'm going to describe today. And some involve my former student, Tim Xie, who is now a postdoc at KITB. And also, at the very end of my talk, I'll mention some ongoing, very recent work together also with John Van Ha, who is a Pappalardo Fellow in quantum information area at MIT. And some early ideas were in this paper I wrote with Chen Ke a couple of years ago. So you have heard yesterday from Michel Devereux's talk about the great progress in superconducting qubits in the very recent years. And in particular, so now it seems that the superconducting qubit technology has made sufficient development that quantum error correction might be around the corner, might be possible. And we will hear more about error correction later today. So the two kind of schemes for error correction are surface code, which has a lot to do with what I'm going to talk about in this talk, and also some sort of a cat code. So now, the kind of qubit I'm going to talk about are made of fermions instead of bosons. So this is a comparison. So a bosonic qubit can be regarded as a two-level system, and in general, it can couple to environment in all possible ways as a spin couples to external magnetic field. So the Z component generates phase error, and the XY component coupling generates bit flips. On the other hand, if we have a fermion energy level that's isolated, decoupled from other fermionic states, then there is a fundamental law in nature that says no process can change the fermion number by 1. So the fermion parity is always conserved in all possible processes. So what this means is that the bit flip error, okay, when that changes the fermion occupation from 0 to 1, is fundamentally forbidden. So if I regard the fermion being empty occupied as a two-level system, then there's only one type of error, okay, which comes from the phase error, and this comes from just the fluctuation in the energy of this fermionic state. So we see that going from boson to fermions, we have reduced errors. Now, in principle, one can do even better. So it's a mathematical fact that any fermion can be written trivially as two real fermions, just like a complex number can be written as the real and imaginary part. So this real fermion is called a Majorana fermion. Okay? It satisfies this reality condition, and different Majorana fermion operators, they anti-commute. So in particular, for a single Majorana operator, gamma squared is identity. Okay? This is a simple algebra of Majorana fermions. Of course, if we are just doing this rewriting, the energy of this fermionic state is equally represented as the coupling between the two Majorana fermions. Okay? So the important thing is that as far as a single Majorana fermion is concerned, it cannot couple to anything. Okay? So the simplest types of interaction arises from coupling between different Majorana fermions. Now, if there is a mechanism, if there is some mechanism that we can spatially separate the two Majorana fermions, okay? And then this will be an ideal situation because this distance between them makes the coupling between the two Majoranas exponentially small, and a single Majorana fermion, as I said, cannot couple to anything. Okay, so this such that the Hamiltonian for this isolated Majorana fermions is identically 0. So yet still, the two together still form a two-level system, because one can always define a fermionic state in this way, and this fermionic state can be empty occupied. Okay? So this is why spatially separated Majorana fermions can be used as a protected qubit. So this idea was proposed by Alexei Kitaev in 2000, and he even came up with a brilliant idea on how one can achieve spatially separated Majorana fermions. Okay? So the model that he proposed is here. It's a model for real electrons, okay, for electrons in solids. And so, as I said, one can always represent an electron as two Majorana fermions. Then these two Majorana fermions may couple within themselves. The two Majorana fermions that descendant from a single electron can couple within themselves, and that leads to a trivial insulating state, not that interesting. However, there's a second possibility that if one can tune this Hamiltonian, then the Majorana fermion can couple between nearest neighbor sites in such a way that there's one Majorana fermion left at each end of this one-dimensional chain. So in this setup, all the Majorana fermions in the interior of this system become gapped. They acquire an energy gap, so they are away from zero energy. So these are physics at the UV scale, which we don't care. If temperature is much smaller than this energy gap, the only degrees of freedom that's accessible are the two zero energy Majorana fermions at the boundary. Okay, and these two are spatially separated. So at the infrared scale, we have achieved a separation of two Majorana fermions. Now, if you look at what this Hamiltonian means in terms of the electronic degrees of freedom, this second type of scenario arises when we have a hopping of electrons from site to site, also a pairing of electrons. So this is why Majorana fermions appear at the boundary of a one-dimensional superconductor, okay, instead of a semiconductor. Now, the particular model I just shown you looks like fine-tuned. One needs to control the coupling constants in the magic to this magic value, but that's really not the case. Instead, the appearance of Majorana fermions on the boundary is a very robust phenomenon. It appears in the extended parameter range, and in fact, whether a Majorana fermion exists on the boundary is directly tied with the topological property of the superconductor in the bulk, something that is known as bulk boundary correspondence. When the bulk is topologically non-trivial, Majorana fermions appear on the boundary. Now, how to make the bulk non-trivial? Well, if we have a spinless superconductor, the weak coupling regime, the BCS regime, is actually guaranteed to be topologically non-trivial. I won't go through the details. So basically, as long as the chemical potential is above the bottom of the band, we have a topological regime. When the chemical potential is below the bottom of the band, we have the strong pairing, the BEC regime, that's topologically trivial. And right at the bottom of the band, this realizes a gap-closing phase transition. Okay? So as long as we stay in the topological regime, appearance of Majorana fermion is, theoretically speaking, is guaranteed. So it's robust. Now, there's one big constraint, which is to realize this topological superconductor, we really require a spinless fermions. Okay, that's what the Kitaev model originally is designed for. Or one need spin polarized electrons. This is because when they are both spin up and spin down species, the pairing between up and down electrons basically leads to two copies of this Kitaev model, because now we have additional spin degrees of freedom. And then each copy, in principle, can realize a Majorana fermion, but the two will couple together, and this removes all the robust zero energy states on the boundary. So the realization of topological superconductor really requires removing the spin degeneracy, and this has been a challenge until recent years. So with Charlie Kane at UPenn, so we came up with the idea that one can really engineer a topological superconducting state using materials that we are familiar with. So a topological insulator has this property that the surface states are spin polarized in a peculiar way, that states with opposite momentum has opposite spin polarization. So when we place a superconductor in proximity with these topological insulators, the superconductivity induces pairing of states with opposite momentum, opposite spin, This is exactly what a conventional S-wave superconductor does. And basically, a topological insulator contributes topology, superconductor contributes pairing, and this naturally realizes a topological superconducting state without any spin degeneracy. So at the vortex core of this two-dimensional topological superconductor, there is a zero energy Majorana fermion. So we need a vortex because a vortex is basically like a boundary between a superconductor and a normal metal. So just like the Majorana fermion at the end of a one-dimensional system, here Majorana fermion appears in the vortex core of a two-dimensional topological superconductor. So then the next brilliant idea came when people realized 2 years later that one can use even simpler materials such as quantum nanowires with strong spin-orbit interaction. So in this case, the spin-orbit splitting leads to spin degeneracy, removal of spin degeneracy at every momentum. However, at Fermi energy, it's guaranteed that there's still both spin up and spin down degrees of freedom because there are 2 right-moving branches and 2 left-moving branches. Now, if one further applies a magnetic field, open up an energy gap, and do gating to tune the Fermi energy within this gap, then we have 1 right mover, 1 left mover with approximately opposite spin. So that's also leads to this kind of helical states, which, if realized, can also lead to topological superconductor. So in 2012, the experiment, the first sighting of Majorana fermion was provided by the Delft group. This is from Leo Kovenhoven and from Sergei Frolov, who is now here. And so they follow this recipe, the nanowire recipe, and in the presence of magnetic field, we see that the zero bias conductance peak appears. Okay, so this zero bias conductance peak could be a signature of Majorana fermions because we know that in a superconducting state, there's an energy gap in the bulk, but Majorana fermions are zero energy states. So with these zero energy states, it enables 2 electrons to enter the superconductor and go into the superconducting condensate. So this leads to a zero bias conductance peak, basically because now electrons can enter the superconductor without paying the energy cost of the pairing gap in the bulk. So then after this experiment, progress in this field become really rapid. 2 years ago, the Princeton group basically used STM to look at assembled atomic chain, ferromagnetic atomic chain in a superconducting substrate. So basically trying to make a Kitaev model atom by atom. And again, you see that the zero energy peak in the conductance appears at the boundary of this chain. Then, even more recently, there's progress, I think very exciting progress, on Majorana fermion in topological insulator superconductor heterostructure. And so this is bismuth selenide, bismuth telluride, topological insulator thin films that's epitaxially grown on niobium diselenide, which is a superconductor with transition temperature around 10 Kelvin. And in the presence of magnetic field, you see that there's a nice array of vortex lattice. At the center of the vortex, there's a zero energy conductance peak. Moving away from the vortex core, we see the full superconducting gap. Moreover, this zero bias conductance peak shrinks as you increase the field. That's consistent with Majorana fermion become from different vortices hybridized with each other. And I think the most striking and interesting results come just in March this year. The same group used spin-polarized STM to look at spin-dependent tunneling. Okay? When the TI film, topological insulator film, is 5 quintupole layers thick, and with a field, applied field, that is smaller than 0.1 Tesla, we see that there's a big difference in spin tunneling when the spin is parallel or anti-parallel to the applied field. Okay? So this is very unusual because if we do the same spin-polarized tunneling on either the niobium diselenide substrate or do this experiment on the TI film that's 3 quintupole layer thick, we don't see any spin-dependent tunneling. Okay? So the absence of spin tunneling, spin-dependent tunneling is what you expect for conventional vortex core states, okay? Because spins are degenerate there. But the Majorana fermion has a special property that it only couples selectively to electron of one spin species. So that's what leads to this. It's consistent with this spin-dependent tunneling. Okay, so now, so with this, with these developments, of course, there's a lot of debate whether these signatures are coming from Majoranas or from other spurious effects. But one can also ask question. So what's the next big thing? Okay, with the appearance of Majorana fermions in solid states, can we probe its topological properties? So we said that Majorana fermions is special in that two Majorana fermions, spatially separated, they share a same fermion state. So can we probe this halfness? Can we probe this non-locality? Okay, that without even spatially separate Majoranas, they are somehow entangled together. And next, can we use the topological properties of Majoranas for quantum computation? So let me first describe the first one, okay, probing the non-locality of Majoranas. So, so the idea is very simple. If we have a single fermionic state, let's say an energy level in the quantum dot, we can connect this quantum dot to electron leads, and we can send the current through a single energy level, and the conductance will depend strongly on the energy of this single fermion states, and that leads to a resonant tunneling. So when tune the gate voltage to make the energy of this level match with the Fermi energy in the leads, we see a conductance peak. This is a resonant tunneling phenomenon that's well understood. So now the question is, if we have a topological superconducting wire so that the bulk has an energy gap, but with two Majorana fermions on the boundary, the two Majorana fermions can be sufficiently far separated so that wave function has no overlap, but we know theoretically the two still form the same state, just like in here. So can we send in current through this entire one-dimensional topological superconductor with non-overlapping Majoranas? Okay. So, it turned out that this is a question that intrigued me for a long time. Finally, I realized that this phenomenon occurs, but only in a regime where the one-dimensional superconductor has a finite charging energy. Okay, so when we talk about the mesoscopic system, adding an electron into the superconductor changes its total energy because the charge is quantized. It's a discrete charge. We cannot just add arbitrarily small charge into a system. And now I'm going to show you that when the bias voltage, the source drain bias voltage, is smaller than the charging energy, then there is a phase coherent transport through the current can be sent through this entire superconductor at energy that's smaller than the charging energy. So this transport is really meditated, it occurs through the Majoranas. And moreover, you see the same kind of resonant tunneling as in here, as you transport through a single energy level, despite that the two Majoranas are spatially separate. So this would be the test of non-locality, something we call teleportation. Okay, so the reason that charging energy is crucial is that there's actually a hidden relation between the Majorana fermions and the electrons. Okay, so basically in the topological superconductor, Majorana fermions are quasi-particle excitations, whereas electrons are the microscopic ingredients that makes the superconductor in the first place. So in a conventional superconductor, the superconducting ground states can only consist of states with an even number of electrons because electrons like to pair. However, in the topological superconductor, in the presence of the Majorana fermions, the ground state can accommodate even an odd number of electrons on equal footing, because electrons can be added into this topological superconductor via the Majoranas. Right? And so every time an electron is added to a topological superconductor, the occupation of Majorana fermions changes, and of course at the same time, the parity of the total number of electrons also changes. So that's why the parity of the Majorana fermions is exactly equal to the parity of the electrons. But we know that the charging energy, basically the electrostatic energy, couples to the total number of electrons, and in this way, they couple to Majorana fermions through this fundamental constraint, fundamental relation. And this coupling exists even when the Majorana fermions are far apart from each other, even when the wave function are non-overlapping. So basically, these Majorana fermions, they are sort of, you can think of it as fractionized degree of freedom, And even though when the wave functions of Majoranas are far away, there's still they're still glued together. They still, remember that they come from the same topological supermatter. So, and the parity of the Majorana fermions are exactly keeping track of the total number of electrons, mod 2, in the supermatter. So, so this is the Hamiltonian that describes the system. There's a charging energy that couples to the total number of electrons. There's a tunneling Hamiltonian, how electron enters to the topological supermatter through the Majorana fermions. So every time a charge is added, from outside, there's this raising operator e to the I phi over 2 that raises the total charge on the island. And now you see that these Majorana fermions are glued together with the total number of electrons through this constraint that I just shown you. Okay? And actually, one can map this problem exactly to the problem of resonant tunneling. Okay? So basically, because at low energy, when the supermatter is tuned near a charge degeneracy state between n and n plus 1 electrons, so this is a two-state system that differ by 1 fermion. It's exactly like resonant tunneling through a single energy level, because when you occupy or empty the energy level, the total charge differ by 1 and differ by a fermion. Okay? So microscopically, what happens is that when an electron enters a topological supermatter, it splits its charge and the statistics. So the charge of the electron is carried by a collective mode, a plasmon mode, but the Fermi statistics is registered in the occupation of Majorana fermions. So that's why this teleportation can occur. This resonant tunneling can occur through Majoranas. Okay, and this effect really requires the bias voltage to be smaller than the charging energy. So it's really a retarded effect. So it's not an instantaneous transfer of charge, but it's a slow process. Okay. In terms of experimental signature, the first test of teleportation would be like this: that if we just look at the normal supermatter normal junction and measure the conductance, if the supermatter is conventional, we will see a conductance peak separated by a charge 2e period, because in a conventional supermatter, the ground states only accommodates even number of electrons. So we will see a conductance when the supermatter is degenerate between having 2n electrons and 2n plus 2 electrons. So you have to shift the total charge by 2 to hit another conductance peak. On the other hand, and this kind of phenomenon was well established a long time ago in the supermatter aluminum, okay, the conventional supermatter. But now in the topological supermatter, what one expects is that this conductance peak become E period because the current is carried by a single electron tunneling, okay, via these Majoranas. So, so very recently, this experiment was performed by Charlie Marcus group. This is exactly the NSN geometry. And in the zero magnetic field, this is this supermatter here is basically aluminum epitaxially grown on top of indium arsenic. Indium arsenic is this quantum wire that I mentioned earlier. And at zero magnetic field, this hybrid system is a conventional supermatter, and you see these conductance peaks with 2e period. But in the presence of magnetic field, it drives the system into a topological supermatter, and you see that the conductance peak becomes E period. Okay. So in particular, this effect persists to wires more than 1 micron long, so it's consistent with transport through spatially separate Majorana modes. In fact, this experimental group have looked at the devices of different lenses, and when the lenses are short, you see that this E period is not exact. There's a small even-odd asymmetry. Okay, this small even-odd asymmetry is reflecting the wave function overlap of the two Majoranas. Okay, and if one plot this hybridization of Majorana fermions, it's even-odd asymmetry as a function of the length of this wire, we see an exponential decay. Okay, so this is consistent with the fact that if we have a longer and longer wire, the wave function overlap of Majoranas will become exponentially small. Okay, it's called exponential protection. Okay. So this is the first Majorana talk. Let me just mention that. If one consider a supermating island with multiple Majorana fermions connected to leads, there's a very interesting topological condo effect basically, this spatially separated Majorana fermions form a non-local sort of a spin degrees of freedom, and this sort of a non-local spin is screened by this whole set of leads, okay, in a very peculiar way. That leads to, theoretically, a non-Fermi liquid phase. Experimentally, it leads to universal conductance at 0 temperature. Okay, independent of the coupling to the leads, the conductance is going to be quantized at 0 temperature. Okay, and we are also, there's beautiful work by Nigel Cooper and his collaborators, and we are also working on this system. And from what I understand, these systems may be experimentally feasible in the next few years. Okay, so how much time do I have?
You have 15 more minutes.
Oh, okay, great. Okay, that's great. Yeah. All right. So let me now move on to the second part of this talk. So we see that when Majorana fermions are spatially separated, they are protected. Okay, the hybridization between Majorana fermions decay exponentially as a function of distance. But in order to really use Majorana fermions to store quantum information, we also need to couple different qubits, right? It's no use to have just an isolated, well, I mean, eventually it's of no use to just have a single qubit. Now, this is where I think things are getting really interesting. So this is something I learned very recently. So please forgive me if I say something stupid. So we have in mind that we encode information using Majorana fermions as physical qubits. Okay, but then because Majorana fermions are coupled together, then errors pop up again. Okay, however, unlike this a qubit made of superconducting qubits or spin qubits, here errors associated with Majorana fermions are really discrete. Okay, so basically the errors come in the form of the fermion parity jumps. Okay, so-called quasi-particle poisoning, and the errors are reduced already by the distance, the spatial separation of the Majorana fermions, and I will show now that these errors are easily correctable. Okay, so what we want is we want to build logical qubits out of this highly entangled state of Majorana fermions, and we do error correction in that way. So what I'm telling you is basically a Majorana fermion version of what's so-called the surface code, okay, which is currently a leading proposal for error correction in conventional qubits, bosonic qubits. Okay, so so here's what we consider an array of Majorana fermions on a honeycomb lattice. Okay, so the honeycomb lattice has a special property that different hexagons they always share an even number of vertices. Okay, so if we design a Hamiltonian, which is like this, it consists of a single type of operator, the product of 6 Majorana fermions at the vertices of each hexagon, and then different hexagon operators they now commute with each other because when you have an even number of common Majorana fermions shared between 2 hexagons, the corresponding operator commute. Okay, so in the ground state, all the hexagon operators have eigenvalue +1, and this is actually a highly entangled state of all Majorana fermions. So if I look at, for example, a fermion parity that's stored in every 2 neighboring Majorana fermions, half of the time it's even, half the time it's odd. So it's an equal amplitude superposition of different ways of partitioning fermion parity in the entire system. And excited states correspond to hexagons with flipped eigenvalues. So, so this gives a way of building a logical qubit. Okay, so if we set the interaction strength on one hexagon to be 0, it basically creates a hole where the hexagon operator can take eigenvalue either +1 or -1, and this defines a 2-level system which we use as a logical qubit. Now, there's a very interesting property that this hexagon can only be flipped in pairs. Okay, so if we, for example, if we divide the hexagon into 3 different colors, the product of hexagon operators of each color that just is equal to the product of all Majorana fermions in the system, which, as I said, is equal to the electron number parity. So because, again, of the fundamental fermion parity conservation in nature, so in the presence of this constraint, this hexagon operator flips can only come in pairs. Okay, and so this hexagon operator defines a logical Z operator, and a product of a string of Majorana fermions defines a logical X operator. The two anti-commute because the string that ends on the hexagon anti-commutes with the hexagon operator. They share one common Majorana fermion. So, so this is, again, because of the hexagon flips comes in pairs, this gives us a way of doing error correction. I think one can think of this error correction as, quantum error correction as classical as possible in this system. So for example, if there is a bit flip error in the logical qubit, this can be just inferred by monitoring the hexagons surrounding this logical qubit. And in this way, because hexagon flips comes in pairs, okay? If there's an odd number of hexagon flips nearby, we can infer that there's a hexagon flip in the logical qubit. So this is important because for quantum error correction, we want to detect errors, but without actually disturbing the logical qubit. So we only monitor regions away from this logical qubit, okay? And likewise, a second type of the phase error can be monitored by looking at how many of these bit flips has crossed this string. Okay. Now, how do we implement this multi-body interaction, 6-body interaction between the Majorana fermions? Well, here's where charging energy again comes into play. So basically, again, so if we have an array of topological schemata, for example, if we use an array of aluminum on top of a topological inserter, that's just one example, applying a magnetic field will generate all these vortices that are trapped at the tri-junctions between 3 neighboring islands, and each vortex will carry a Majorana 0 modes. And then the charging energy, very roughly speaking, again, charging energy couples to the total charge on each island, and the Majorana degree of freedom also is just equal to the fermion parity, roughly speaking, on each island. And that's why this charging energy projects into the low energy, the charging energy projects onto this multi-body interaction between the Majoranas. Okay. And one can also measure these occupation of the Majorana fermions using microwave photons. This was proposed by the Carlo Banneker's group and by Leonard Glassman at Yale. And in a conventional superconducting qubit, the energy levels of the qubit basically corresponds to states with different charge or state with different flux. And here, what happens is that each energy level of the superconducting qubit is actually a cluster of states with different occupation of the Majoranas. Okay, so if one think of the superconducting qubit as an artificial atom, a topological superconducting qubit with Majoranas basically makes each energy level comes with a fine structure. Okay, and the splitting of these Majorana states can be monitored by the energy gap in the microwave measurement. And for example, in this experiments on a conventional schemata, you see 2 branches of energy levels. These are actually corresponding to states with different fermion parity. So the same kind of measurement can be used in principle, we think, to monitor the states of the Majorana fermions. So the idea is that if we have a topological schemata, then each of these energy levels would split into a cluster of states, okay, with characteristic dispersion. Okay. And measuring these energy basically is a way of measuring the state of the Majoranas. And so this kind of a qubit that I described, you can regard it as a sort of a Majorana fermion integrated with a charge qubit. Okay. There's also very nice work by David Pecker here on coupling Majorana fermions to flux qubit. So I think this is really something that's really needed in this area. Basically, we need to integrate Majorana fermions with superconducting qubits. Okay, so then I'll very quickly go through that the rest of this Majorana surface code. So basically, in principle, one can also do gate operations in addition to error correction. In particular, C0 gate, the 2 logical qubit gate, actually in this setup corresponds to basically dragging a hole around another hole of different color. Okay, and So what this C0 operation does really is basically detecting a mutual statistics between anions. So each of these hole is a topological excitation, and they have pi mutual statistics. And of course, the way the holes are dragged, just like in the conventional surface code, is basically through a sequence of measurements. Okay. And the Hadamard gate can be achieved by basically what we call in condensed matter field nowadays anion transmutation. Basically, one can find ways of turning holes of one color into the other. Okay, so that changes the sigma z to sigma x. Finally, the challenge is to implement the single qubit S and T gates, and here we are following the same idea as the conventional qubit surface code. We rely on magic state distillation, and we are still thinking whether there are ways of improving this. So let me summarize. So the Majorana Fermions surface code basically is a Majorana Fermion version of the surface code, but I think there are maybe some advantages here. So as you see that we really have a way of engineering the six-body or the multi-body interaction between the Majorana Fermions. Okay, that's something that's not easy to achieve in the usual surface code, and this kind of a non-local multi-body interaction is generated from the charging energy. Okay, without relying on the wave function overlap between Majoranas. And in this setup, the errors are already suppressed by the presence of energy gap. So at a low temperature, much smaller than gap, error rates are suppressed by the distance between the Majoranas. That leads to increased error tolerance, etc. So I won't have time to go over this, but really, if we actually now theoretically generalize this two-dimensional Majorana code into 3 dimensions, we place Majorana Fermions on a cubic lattice and replace the plaquette operator by this kind of 8-body cube operator. This actually turned out to be very, very interesting from a theoretical point of view. This is a local Hamiltonian that leads to point-like excitations that are fundamentally immobile. Okay, this is a new kind of topological quantum order. We call these immobile excitations fractons. So it's a fraction of an anion. Okay. So let me just end here. I think that really in the last few years, there's really a lot of developments in the interdisciplinary area between theoretical physics, quantum materials, and quantum information, and I think it's really a lot of opportunities and a lot of room for further development. Thank you.
We have time for